in order to calculate uncertainties, it's not as simple as it looks. That's the thing I really wanted to show you today. So if you're going to actually try to calculate them, you need to understand a little bit about how to work with these uncertainties. And I'll give you a really, really simple, dumb example, and I'll show you how to use it in two different methods. And after that, I'll show you a real example from an exam. So let's just say you're doing a measurement. So you're measuring a distance here. And you're measuring your distance, let's just say is, so I'll just maybe rewrite it like this. Maybe it's a bit easier here. So I'll say, so your distance is 10 meters, but your uncertainty on your distance is plus or minus 1 meter. And you have the time is 5.0 seconds, but the uncertainty on your time is 0.2 seconds. I think it's maybe clearer to have it written big like this. Okay, so first of all, it's a good idea to double check that your uncertainties are correct. Is it one non-zero number? Yep, good. And do the digits match? Are you rounding on the sort of ones digit? Yeah. And here it's one non-zero number as well, the 0.2, and they're both being rounded. They're both sort of, you get one digit after the decimal for both of them. So that looks okay. There's nothing sort of weird about this. You're measuring distance and a time, and you want to know the speed. Now, if you remember just simple dumb equations for speed, speed is just distance over time, right? Or displacement over time if you want velocity. Okay, so then you can say, all right, then fine. I mean, speed then is just d over t, so that's just 10 over 5. So that's just 2, right? It's just 2 meters per second, right? But is it? Here's the problem. In this kind of example, if they're giving you uncertainties, you're fully expected to figure out plus or minus what do you do here. So how do you actually do this? And remember what I showed you before. If you've done this like this, remember it's the uncertainties that then drive the number of significant figures you're allowed to use here. So we don't know if we need to go 2 or 2.0 or 2.00 or 2.000 or I don't know. So let's just see what we get. So I'm going to show you two different methods to do this. So the first method is called the largest smallest method, or at least that's what I like to call it. What I mean by that is it's a really, really simple, by the way, I just cut and paste the same example just so we have all the numbers there. So the largest smallest value method is just that. Just try to find out what's the biggest value you could possibly have with your uncertainty. Not with your uncertainty, I mean for each of your values. And I think I'll explain this. In context, it's going to make more sense. So for example, let's just take a look at this right here and see what we do here. So if we have a distance, just think about this here. So we have a distance here. Maybe I'll draw a light blue here. So the distance that I'm measuring is actually, like I said, it's 10 meters plus or minus 1 meter. That means it could be as small as, think about this, 10 minus 1. So it could be as small as 9 meters, but it could be as large as 11 meters. Just like your time, right? Your time is 5.0 seconds, and it's plus or minus 0.2. So that means your time could be as, let's see, as small as 5 minus 0.2, which is 4.8 seconds. And it could be as high as 5 plus 0.2, which is 5.2 seconds. This is sort of your range of values for d and for t for your time. So if you think about it, if you're looking at a velocity, or a speed, sorry. So this is right here is the equation you're looking for, right? You're looking for speed. Let's just say, so the speed then is distance over time. How do you get the biggest value? So I'm trying to find out basically largest v, and I want to get the smallest v. So I'm trying to see like which different things, like what's the absolute largest I can get, what's the absolute smallest I can get. To get the largest value of v, think about it. I want the so that means so largest distance here. So in this case right here, I would use 11. And I would divide that by, let's see here, in this case right here, because it's a denominator, you want the denominator to be the smallest value, because the smallest, a big number divided by a small number is the biggest thing you can get. In this case, I want the smallest time. So in this case right here, I would use the 4.8. And I just use my trusty calculator with that, right? So I'm using an TI-84, but some people use the Inspire or the Casio. There's different choices, but I'll just use my simple little TI-84 here. So if I do this right here, I get an answer of 2.2916, let's just say, meters per second. And if I want the smallest value of v, I do the opposite. So there I'm going to use the smallest value of d on the top. So in this case, I'm going to use 9 meters. By the way, this is in seconds. I'm going to use the largest value of time on the bottom. So I'm going to use 5.2 seconds. So that means there I get 9 over 5.2. So there I get, notice these are calculated values. There's lots of digits here. I don't really know where to stop. I'll just stop at like 4-ish because I probably don't need to go much further than that. Meters per second. So do you see I've got these two values? I've got the largest value and I've got the smallest value. So how do I actually deal with this? That's where I use this sort of magic equation here. This equation I need to use is this, right? That the uncertainty, this is the one here I'm going to use. So the uncertainty is going to be the largest minus the smallest, and it's going to be half of that. So in this case right here then, the uncertainty, and I'm going to write it as delta because that's what we use. We use delta V in this case here, uncertainty on the speed. Delta V in this case here is going to be the largest, which is 2.2916, minus the smallest, which is 1.73077. You can use lots of decimals if you want, doesn't matter. All that divided by 2. I'm going to do that on my calculator. So 2.2916 minus the 1.73077, divide that by 2, and I get an answer of this. I get delta V equals 0.28045, let's just say, something like that. So first of all, what do you do with this? Do you remember I was showing you before? Your uncertainty on V needs to have just one non-zero number. So I'm going to take my answer for delta V here, and I'm going to make it delta V equals, let's see, I'm only allowed one non-zero number. So I'm going to have to round right here. And the 2.8 becomes the 8 forces this number to go up. So in this case, it's just going to be 0.3. So now I'm finally ready to have my conclusion here, which is that the speed then is going to be grand total here of, let's see now, it was, what did we say it was? Well, it's 10 divided by 5, so that's 2. So in this case, it's going to be 2.0 plus or minus 0.3 meters per second. This is going to be my final answer. So do you notice what happened here, right? This is it. I'm done. So what happened is I calculated the delta V, the uncertainty on the speed. I forced it to be one non-zero number. And then from there, I can tell how to round because I can only use 1 after the decimal. That means I'm only allowed 1 after the decimal here. So that's how you can do it. Now the other method uses the equations. So these are the equations from your data booklet, and you can actually look these up. They look just like this on your data booklet, this one and this one. So I just want to show you those ones. So for example, what this tells you is if you're measuring, so this just tells, the notation looks a bit weird, and not many people know to look for this, but if you look at your data booklet, it's actually there. This is there for you. So what you can do then is you can take a look and say, okay, the uncertainty on a value, given that you have something plus another thing. In this case, A plus B, or it could be A minus B. I hate the way they wrote it because it looks like it's A plus or minus, as in if B is the uncertainty. I don't mean that. I mean like if Y equals A plus B, then the uncertainty on A and the uncertainty on B, you just add them together, you get the uncertainty on your total value. Hope that makes sense, because if you actually take, oh, I don't know, let's just say you're taking a length like this, you take another length like this, the uncertainty on both those lengths, you know, just add the uncertainties and it should make sense. Also, if you're subtracting, so that's why if it's A plus B, or if it's Y equals A minus B, the uncertainty, this delta Y, is going to be the same thing. You just add the uncertainties, whether you're adding or subtracting the values. This one, however, looks a bit more complicated, but it's totally doable. This says that Y equals AB over C. What this means is if you're multiplying or dividing, or even both, you can be multiplying and dividing in an equation. Here they show you like you have Y equals something times another thing divided by another thing. They tell you that the uncertainty on your Y, it's not quite just isolated for uncertainty. Do you notice it's delta Y over Y? In other words, the uncertainty divided by its own original value is going to be equal to the uncertainty on the first thing divided by itself, plus the uncertainty on the second thing divided by that thing, plus the uncertainty on C divided by C. So in this case, I'm going to show you the example that we had. Wasn't it just, it was just V equals D over T, wasn't it? So do you see we have an equation just like this? So we can apply this method here, and you'll see this method is much faster. So if I want this, then I know that delta V over V, because I'm going to use this second method here. I'm going to use that one. So if I want, that's because I have something divided by another thing. So I'm doing dividing and multiplying here, or multiplying. So in this case, what do I do here? I know that delta v over v, because I'm using this function here, I'm using this delta y over y, in this case delta v over v, is just going to equal to the uncertainty on distance divided by itself, so divided by the distance, plus the uncertainty on the time divided by the time, and that's it. So in this case here I can figure it out, right? So the uncertainty on v divided by v is going to be, let's see, what's the uncertainty on the distance? It's 1 meter. See, that's over there, it's 1, divided by 10, because that's the original distance, plus the uncertainty on the time, which is 0.2, divided by 5. That wasn't so hard, was it? By the way, keep in mind, you also know your v, actually, so I should probably, I'll just leave it. So therefore, keep in mind, I have v, don't I? So I have 1 over 10 plus 0.2 over 5. But I also, if I want just delta v, I have to multiply this v. I have to put it to the other side. So I'm going to multiply it here. And what's the v value? What's the speed? Remember, it's 10 over 5, which is 2. So this is why I get the actual uncertainty here. We're going to call it later, we're going to call it the absolute uncertainty. That's what I have here. The absolute uncertainty on this is going to be 1 over 10, which is 0.1, plus 0.2 over 5, all that times 2. So in this case right here, I get, hey, good news, I end up with 0.28. Hey, isn't that what I had before? So that's why I'm going to end up with, I mean, look at the example I had before. Remember I had that delta V was 0.3? I get the same thing here. Look, my delta V, let me just look at it here. So my delta V then is going to be, well, I can't use 2 digits. I'm only allowed 1 digit to use it, and 1 non-zero number. So in this case, this has to be 0.3 meters per second. Therefore, my final answer then is V equals, remember it's 2, and again I know to round it to put 1 decimal after, one value after the decimal. So in this case I'm going to say 2.0 plus or minus 0.3 meters per second. Aha! That's how we do it. And I have an example for you, another one, just to make sure it makes sense. So this is the final answer here. So if we do another example, so here you measure, and this is something like, well, this is something from an exam here. So you measure the length of a cube. In this case, so remember what a cube looks like. Cube looks like this, right? It's going to be a nice cubic, well, I'm not a lousy artist, but we'll see here. This is a cube. And we have the length of a cube to be 2 meters. So this is 2 meters here, but so is this, because it's a cube, right? It's got the same length, width, height. And we know the uncertainty is 0.001. So we know that L is 2.00 plus or minus 0.00, 0.01 meters. This is what we know. We want the volume. And how do you find the volume? There's a couple ways of looking at it. I mean, there's another equation on your data booklet, actually, that has it like what to do if there's a power here. You're just supposed to put the power in front. But I'll show you that that's going to be sort of, we're just sort of going to know what to do here. You'll see what we do here. So what we're going to do, we're going to get an equation for the volume. The volume, maybe I'll write volume just so you know, it's going to be the length times the length times the length, or length cubed, right? But in this, I'm just going to split it up just so you can see it more obviously. I'm going to use this rule number 2 here. This y equals AB over C is just delta y over y plus delta of all the things divided by themselves here, and add them together. In this case right here then, that means I'm going to say delta V over V, delta volume over volume, is going to be equal to then just delta L over L plus delta L over L, because I've got it again, and again delta L over L. That might get kind of annoying, right? So that's why what you can say instead is you can say that equals 3 times delta L over L. And this is actually the equation you're supposed to get to. That's another equation on your data booklet. It says, in this case right here, you know, if we're going to do this, we could say it's L cubed. And you could say what happens is the 3 comes in front. So basically that's just sort of the same rule happening here. So 3 times delta L over L. Because we have it this plus this plus this. So in this case right here, then we have delta volume, remember, over the volume is going to be 3 times the uncertainty on the length, which is 0.01, divided by the length itself, which is 2. And I have it times 3 right here. So in this case right here, we can figure it out. Oh, and we have the volume itself. We actually have to figure out that because we want delta volume by itself. We want the absolute uncertainty. So the uncertainty on the volume is going to be just this right here. So this is 3 times, well, that's 0.03. Let's see. I just multiply this out, right? So 3 times 0.01, all that divided by 2. And I'm going to say that thing right here, so that's 0.15, sorry, 0.015. But remember, I got to multiply that. Here I had delta volume over the volume. So that means I have to multiply by the actual volume. The volume, of course, is going to be 2 times 2 times 2, which is 8. Because that's actually the volume. The volume is actually 8. So then I do this number right here times 8, and I get delta volume is going to be 0.12. And remember, you're only allowed one non-zero number. So in this case here, I'm going to state then that the uncertainty on the volume is going to be 0.1. In this case, meters cubed. So what do I do with that? I have my final answer. Now I'm ready. I can then state that the volume is going to equal 8, because that's what L times L times L is, right? 2 times 2 times 2 is 8. And I know how many figures to put in. I know how many values after the decimal I'm allowed. Because my uncertainty is 0.1 meters cubed, then I know that I'm only allowed 1 after the decimal, so that means I know to force it to be this. This is your final answer. So see, you can solve exam questions too. They might seem annoying, and once you've done a lot of them, you'll see you're a lot quicker at them. I just wanted to show you all the steps.